Okay, today's learning target is to be able to analyze characteristics of polynomial functions. And really what we're doing is we're going to add a little bit of new features, and then we're just going to try and make sure that we've put all of the pieces together so that we can not only tell different features of a graph by looking at it, but also look at an equation or a function or be given different information about a polynomial and be able to make a sketch. So we're going to start with some stuff that we've talked about before. We're going to answer questions 1 through 3 together. So the first question is the graph positive or negative, and how do you know? And when we ask if the graph is positive or negative, we're really talking about the lead coefficient of our function. And the lead coefficient of our function, we've learned, is tied into the right end behavior. So since this right end is rising, right? So the right end rises. We know that our lead coefficient of our function should be positive. So in this case, we'd call this graph positive because the right end rises. And the second question is the degree of the function even or odd? And so we know that we can tell whether or not the function is even or odd based on both ends, right? So if the function were even, the two ends would be doing the same thing. So if the left end was also rising, we would have this would be an even function. But since the left end falls, this is actually considered an odd function. And then finding the local maxima and minima for the graph. Notice I say local because there are no absolute minimums or maximums. So if I look at this particular graph, it looks like I have two minima, one here, local minimum, and one here. And the first one, the leftmost minima, has a y value of 0. So I'm just going to write local minima at y equals 0, and y equals this one on the right. Looks like it got down to these counting by 20s, so maybe y equals negative 80. And then we have some local maxima at y equals these two. The leftmost one, this one looks like it gets up to, oh, sorry, these were counting by 10s, not 20s, my bad. So maybe that's negative 70. And then, so then this one up here, this guy looks like gets to 10, 20, positive 30. So y equals 30, and y equals this other one highlighted over here. It's in between the 10 and 20 marks. So let's say y equals 15. Now, it's hard for us to tell. We could use the graphing feature to come up with the local minima and maxima exactly, but just looking at a quick sketch of the graph, that's what it looks like from there. So just a quick summary of things that we've already learned about polynomials. We know that the lead coefficient tells us what the right end behavior is doing. As in, like, if it's positive, then the right end rises. If it's negative, then the right end falls. Okay, and the degree will tell us quite a few things, actually 3 things. The degree will tell us what the left end behavior does, because if it's even, the left end will be doing the exact same thing as the right end. If it's odd, the left end will be doing the opposite of whatever the right end is doing. Also, the number of the degree, right? So if the degree was 5, that will tell us our maximum number of real zeros, because if my were degree of 5, then I would have exactly 5, or a maximum of 5 real zeros, also known as x-intercept, solutions, roots. Okay, and then also the degree, it tells us the maximum number of turns. So if the degree were 5, we'll use that same degree as before, then the number of turns, the maximum number of terms, has to be one less than that degree. So if the degree were 5, then the max number of turns is 4. Okay, so we're going to take that information, and we're going to start answering different questions about these graphs. Okay, so our goal is to circle all the functions that could match these graphs and explain why they could or why they couldn't. Okay, so for graph number 4, okay, I'm looking at these 3, right? So number 1, number 2, and number 3. Okay, f of x, g of x, and h of x. For graph number 4, okay, there's a couple things that I'm going to talk about right away. I want to notice that both ends are falling. So since the right end falls, that means I have to have a positive lead coefficient. And since both ends fall, this should be an even degree. Okay, so I'm going to use that to kind of look at some of these functions and decide if those would match. So number 1 has a negative 3x to the 5th minus 2x squared plus 4x plus 7. So the lead coefficient is -3 and the degree is 5, right? Because the highest exponent is 5 here. So since it's an odd degree, number 1 cannot match. Okay, so it can't match to number 1. We'll move on to the second one. Okay, the second one, it looks like I've got, and figuring out the degree is going to be interesting. So let's talk about how we can kind of figure out the degree and lead coefficient kind of quickly. Okay, if without actually multiplying all this out, okay, I want to talk about what it would be just the lead coefficient. So I'm going to take just the first term in each one of these parentheses, okay, and multiply it out. So I've got a -1 times x times x times x times x squared times x. All right, so let's write that out. It's -1 times x times x times x times x squared times x. And that would be negative 1, 2, 3, 4, 5, 6, negative x to the 6th. Okay, so this is an even degree with a negative lead coefficient. So it could match with graph number 2. Okay, and then graph number 3 is also, the lead coefficient is -3 and the degree is 4. Okay, so it could right now match to numbers 2 and 3. Now I'm going to go a little bit further with this and talk about the number of real zeros. Okay, remember my degree matches the maximum number of real zeros that I can have. Okay, so if I look at this graph, I've got 1, 2, 3, 4, we'll talk about that in a second, and 5, at least 5 real zeros. At least 5. So this is a degree of only 4, so it cannot be number 3 because I need at least 5 solutions. So number 2 is the only one that could match number 4. Okay, so we're going to go with, it should go with g of x because g of x has a negative lead coefficient, an even degree, and could have 5 real solutions. Cool. All right, let's try another one. Actually, before we try another one, I want to have a quick conversation about this solution right here. So this solution right here, if you notice, this is something we had a conversation about before. This is what we call a double root. So anytime we have a solution that hits the x-axis and bounces back off, that's what we call a double root. And so if I look at something like y equals, I'm going to go to a quadratic that you guys have solved before. Y equals x squared minus 6x plus 9. Okay, when you guys solve this one, if you were to use the quadratic formula, you would have found that doing b squared minus 4ac, which is the discriminant, gives you 36 minus 4 times 1 times 9, which gives you 0. And so based on that information in the last unit, you would have told us that this has one real solution. Only one real solution. And let's see how that one real solution actually appears on the graph. Okay, that one real solution comes from me setting this equation equal to 0. If I were to factor this, it factors into x and x, and to get positive 9 but negative 6, I'm going to make -3 and -3. And so my one real solution, I get x equals 3 and x equals 3. Technically, this is 2 solutions, okay, but it's the same one twice. So what we weren't too picky about saying is that it's one unique real solution. And so what I'm seeing is a double root. In other words, the solution of x equals 3 is happening twice on that x-axis, okay? And so what I'm getting, I know this graph has a y-intercept of 9 because of the c value, okay? And so a quick sketch of this tells me this graph should open up, bounce off the x-axis at x equals 3, and then go back up. Okay, and so this is the solution of x equals 3 actually occurs twice in my function. So if I go back to this one on the graph here, this had a double root here. In other words, I can count that as this would have had 1, 2, 3, 4, 5, and 6 total real solutions. So I'm going to use that as I start looking at some of these other ones. Number 5, I look at this graph. Okay, let's talk about what features it has so we can talk about which equations might work and which ones might not. Okay, so this particular graph has it rises on the right, so that needs a positive lead coefficient. Okay, it falls on the left, so that means it should be an odd degree. Okay, and it has 1, 2, 3 unique real solutions. Okay, so my degree has to be at least 3. Okay, so let's look at this and look at f of x, g of x, and h of x again. Okay, f of x, if I go through this and try and figure out the degree, if I multiply this out, it's going to be 0.5 times x times x times x. So that would be 0.5 x cubed would be my first term in f of x. And I don't really care what the rest of it's going to be because I just really need that first term. So I know this has a positive lead coefficient, it's an odd degree, and the degree is at least 3. So f of x is possible. Let's look at g of x. G of x is negative 2 times x times x times x. So g of x is negative 2x cubed. Plus, who cares what the rest of it is? Okay, because the rest of that won't give me any sort of information about what, it doesn't tell me much more about the graph. Okay, and so since that's the case, this is a negative lead coefficient, so g of x is out. And then h of x is going to be equal to 2 times x times x times x times x. Okay, so that's 2x to the 4th plus blah, 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 blah. And that's an even degree, so h of x is out. So this one must be f of x because it's the only one function with a positive lead coefficient and an odd degree. Okay, let's go ahead and try one more. But this time we're going to switch it up because these ones are matching 6 and 7 are similar. I'm going to let you guys do those on their own. So let's try 1 or 2 more where we actually look at, I give you some information about a polynomial and then you have to make a sketch of it. So I like number 9 specifically. So we'll start with number 9. I want to draw a 5th degree polynomial with 3 real zeros. Okay, so 5th degree tells me that the ends should be doing opposite things. Okay, it also tells me I can have at most 4 turns. I can have less than that, but I can't have more than that. Okay, and I can have at most, oh wait a second, I got more information about the real zeros. I only want 3 real zeros. So I want 1, 2, 3 x-intercepts. Okay, I didn't say anything about what the right side does or the left side does, except for that they should be doing opposite things. Okay, so I got to go through those 3 points on the x-axis, and then let's let the right side go up and the left side go down. Now, you might do that differently, and that's totally fine. Okay, and then I want 4 turns in here. So let's go 1, 2, 3, 4, 5. Wait, 1, 2, 3, 4. I'm good. Right? So here's 1 turn right here, here's a 2nd turn right here, here's a 3rd turn right here, and there's a 4th turn right there. Okay, I made an extra little loop down here because I wasn't allowed to touch the x-axis again, otherwise we would have more than 3 real zeros. Okay, and that's it. I've got all of my criteria covered. Let's try 11 together, and then I'll let you guys go ahead and do the other ones. So 11 says I want a cubic. Okay, so cubic meaning it has degree of 3. Okay, so that means I can have at most 2 turns. Okay, I've got 1 real zero. So here we go, 1 real zero. And I want 1 relative max. Okay, so at some point my graph has to go like this, right? So I have to have a relative max. So let's make my graph go like that. Okay, and I'm not specific about that degree if it needs to be, it has to be a degree of 3, so that means that I have to have opposite ends. But it doesn't tell me if the right end is going up or if it's going down. So what I'm going to do to make this easy on myself, okay? Because I only want